let me pick up where I left off yesterday with this power series. This is going to be a short video, and then I'm going to make another one for the next topic so that I don't get cut off on YouTube. All right. We talked yesterday about the idea that all of these infinite series are going to be polynomials, are going to be power series. Polynomials where you have all the powers of x. And the last thing I said before we left was we were talking about intervals of convergence. And I said that there are a couple options for that interval in any given series. Every series ever is always going to converge at its center. And all of the series that we've seen so far are centered at 0. Soon I'm going to show you what it looks like when it's not centered at 0. Outside of the center, you've got three options. Either it converges on some finite interval, like the geometrics that we saw that converged between -1 and 1 or -2 and 2. If that is the case, it will always be symmetric. So you will always see an interval that's like -2 to 2. You will never see an interval that's like -2 to 5. Okay? Not if it's centered at 0. If you have an interval from -2 to 5, then the center is the exact middle between -2 and 5. Okay, which is what? 1.5, right? So if they give you an interval, you can know the center. And if you know the center, then you know that it's symmetric on either side. Another option is that it converges for all values of x, and there are some pretty important series that have that property, and they're awesome. Those are the ones that we literally memorize so that we can just use them and we don't ever have to worry about writing them. And then last but not least, the most worthless of them all is that they converge nowhere outside of the center, in which case they're completely stupid and useless. Okay, so let's take a look at a couple examples of these. So if you have that finite interval of convergence, see again, -1 to 1, that means that its center must be at 0. This is what that's going to look like graphically. You can see from the middle as you move out towards -1 and out towards +1 that the polynomial is hugging the original curve really tightly, and then obviously at 1 it's a train wreck. The polynomial goes up and the function goes down. On the other end, the polynomial shoots to -infinity and the actual function is going to have an asymptote. Now, this is an odd order polynomial, but even if you added another term and it was fourth order, then this would be shooting up on the other side. So it would still, as soon as it gets near 1, it's going to diverge. This is a -infinity to infinity type of situation where the function, the more terms you add, the closer and further out it hugs. The series for sine and cosine are like this. The more terms you write, the further out it'll go, and you can write a really, really long series that has a really, really huge interval of convergence. It's really cool. This is a bizarre example of one that is only ever going to converge at the center. In other words, if x is 0, then all the terms will be 0, and your polynomial will match your series. This is the only time that happens. Because as soon as you have an x, anything bigger than 0, and you start adding terms in here, this factorial grows so quickly that it just diverges as soon as it leaves the center. So as you can see, when I graph these partial sums, they're all over the place. So this has an interval of convergence of one single number, and that is the center. That is the only place that these partial sum polynomials match what the actual function would look like. Okay, so when you're looking for interval of convergence, which we did on that, you did a little bit of on that last homework, if it is geometric, all you need to know is what the r value is, and as long as you keep that r value between -1 and 1, you're good to go. So in this case, our r value is -x. And notice this is a minus and this is a plus. So as long as I keep -x between -1 and 1, I'm good to go. So in other words, I need the only values for which this series is going to work is if x is between -1 and 1. We call that its interval of convergence, IOC. And notice when you look at the graph, again, Here's my function. Look at my polynomial. Okay. Between -1 and 1, it's looking pretty good. Outside of that, it's garbage. Look at this one. And here in this one, your a is 1, your r is 2x. My r value is 2x. So I have to keep 2x between -1 and 1. Ooh, that's not supposed to be there. Sorry. So if I want 2x kept between -1 and 1, solve that double inequality, that compound inequality, you get that x has to be somewhere between -1/2 and +1/2. In other words, my interval of convergence is much smaller now. It's the thing I'm multiplying by is bigger, so my terms are going to get bigger more quickly. And you'll notice here, your polynomial is pulling away from your function much sooner. This interval of convergence is only from -1/2 to, or -1/2 to +1/2. Again, notice that it's centered around 0. It will never not be centered around 0 unless your polynomial isn't centered at 0. Okay, so the final thing that we have to talk about is what happens when they're not geometric. Because if a series isn't geometric, then telling if it diverges or converges is a much more complicated question. So there is a trick that in practice is not ideal, but every once in a while the AP brings it up. So I just thought I would throw it out there to you. You are allowed to take an integral of a series or a derivative of a series, term by term, to create a new series. And your new series will behave like your original series. So in other words, if I have a series for f of x, I'm going to name it series smiley face. If I take the derivative of f of x, I get a new series. I'm going to call it series smiley face prime. If this guy converges, this guy converges. If this guy diverges, this guy diverges. So again, it's not really ideal as far as finding a series, but AP brings it up, and I'll show you exactly what I mean here in a minute. So if we look at this, this is a nice geometric series, right? Here's my a value. This is an a over 1 minus r, where your a is 1 and your r is x. So what I can do is I can come over here and take the derivative of 1 over 1 minus x, and I can take the derivative of this series term by term and create a new series for a new function. Okay? So if I take the derivative of 1 over 1 minus x, I get 1 over 1 minus x squared. Don't wait a minute. That's my globe. Am I missing a negative here? No, I'm not. Okay, I'm good. So 1 over 1 minus x squared. And notice here, term by term, when you take the derivative of 1, it goes away. It's 0. Take the derivative of x, it's 1. Take the derivative of x squared, it's 2x. Take the derivative of x cubed, it's 3x squared. So I now have a new series that I got from this one, and it represents this new function. Now, if they said to you, hey, can you write me a series for 1 over 1 minus x squared? I seriously doubt that you're going to go, oh, I know what I'll do. I'll write this series for 1 over 1 minus x because it's geometric, and then I'll take its derivative. Like, you're not going to think of that. What's going to happen is they're going to give you a series, and then they're going to specifically ask you for the derivative of it. You can go the other way as well with an integral. And I know everybody remembers the integral of 1 over 1 plus x. That's right, the ln of 1 plus x. Very good, I am impressed. Okay, and if I integrate that, then I can integrate the other side term by term. Again, the natural log of 1 plus x is the integral of this side. The integral of 1 is x. The integral of x is x squared over 2. The integral of x squared is x cubed over 3, and so on and so forth. So now I have a series or a polynomial that represents the natural log of 1 plus x. And check it out. Here's my natural log of 1 plus x, and here's that series. Here's that polynomial approximation. Again, it's looking pretty good between -1 and 1. And outside of that, it's looking pretty bad. Okay, so this is just, I just want to show you a couple ways that AP sneaks the derivative and the integral in here. You'll notice in this top one, it says the Taylor series for a function. We'll talk about Taylor series next. And they give you the rule for the series up here. And they tell you it converges to f of x. In other words, they're telling you, I'm giving you the series for f of x. And then notice down here in part B, they say find the first three non-zero terms for f prime. So in this case, what I would do is write out the first several terms of this. Now this looks pretty complicated, but it's not terrible, right? When I plug in n equals 1, the first term of this is going to be negative 1 squared, so it'll be positive, 2 to the 1 over 1, and then x minus 1 to the 1. So the first term of that is 2x minus 1. When I put in a 2, it'll be negative now because this will be a negative 1 to the third. 2 to the 2 over 2. So 4 over 2. And then x minus 1 squared. When I put in a 3, that one will be positive. It'll be 2 to the third. So 8 over 3, x minus 1 to the third. Now notice they only said the first 3. So there's my first 3 terms. This is the first 3 terms of f of x. If I want a series for the derivative of f prime, I'm just going to take its derivative. The derivative of 2x minus 1 is just 2x. The derivative of 4 over 2x minus 1 squared is 2 times 2x minus 1 to the first. The derivative of 8 thirds x minus 1 to the third is 8 thirds times 3 x minus 1 to the second. Now, could you simplify that? Heck yeah. Are you going to? Not a chance. Circle and be done. Okay. Okay, let me show you another one. Okay. Here they say the function g has derivatives of all orders, Maclaurin series. We'll talk about that here in a minute. Next video. They give you the rule for the series, and look how nice they were. They gave you the first 3 terms. And then down here in part C, they say write the first 3 non-zero terms and general term for the series of g prime. So again, if this is g, which they gave you, then g prime is going to be, this is 1/3 x, so it's just going to be 1/3, minus, you have a 1/5, and then a 3x squared, and a 5x to the 4th. Now, they want the general term, so you're going to have to figure out how to write a rule for this. But it's actually pretty straightforward. Notice the bottom is consecutive odd numbers. So I can use like a 2n plus 1 for my denominator for that number there. And as long as I start at n equals 1, that will give me my first denominator of 3, my second denominator will be 5, my third denominator will be 7. And then to generate these other terms, like this is an x to the 0, so you have even powers. So you can do an x to the 2n, that'll get you your even powers. And then you just have to generate the odd numbers. And again, it's like 1 less. So instead of 2n plus 1, I believe a 2n minus 1 will do it. So when I put in n equals 1, I'm going to get a 1 over 3. Oh, hold on. I got to do this. Yeah, when I put in an n minus 1, or an n equals 1, I'm going to get a 1 over 3. I'm going to get an x to the 0, and then I'm going to get a 1 right here. That'll give me my first term. When I put in a 2, I'm going to get a 5 here, 1/5. I'm going to get an x to the 4 minus 2, x squared, and I'm going to get an x to the, or then I'm going to get a 3 here. So that's going to generate this term. The only other thing we're missing is the plus minus, and we get that by doing a -1. Let's try -1 to the n and see if it works. When n is 1, it's negative. Nope. So I'm going to fix it by going like this. Now when n is 1, it'll be positive. When n is 2, it'll be negative. Okay. We can talk more later about getting this from this, But for now, ta-ta.